Okay, so welcome to the lecture of this finite volume method. So far what you have seen the mesh topology, information connectivity, data structure regarding both structured and unstructured, and just in the previous lecture we stopped at the calculation of the unstructured algorithm, where you have seen that example what we have taken, that if you this two dimensional system, this is the global picture of each elements and the what data structure required, and we have discussed the pseudo algorithm also. But importantly, so what one has to keep track of the elements essentially for the unstructured system and unstructured grid. So, you have a huge data structure requirement or data structure handling. So, here you need elements both local indexing and global indexing. Then you have connecting faces, where you have a local indexing, you have a global indexing. So, which will take care of the sign of surface vector S. Okay. So, then you need to have the information about nodes. Again there would be local indexing of the node, there would be global indexing of the node and other information. So, if you see the involvement or the handling of the data structure for a programmer point of view is quite heavy. It is not that straightforward that you have seen for the structured cases, because structured cases everything was nicely ordered. So, as you go by I and j loop, you could figure out the I and j element with a global numbering. So, this is your global indexing, but unstructured case the complete scenario is different. Here one has to have elemental connectivity starting from local to global, you have a phase connectivity local to global, which also includes the sign of the surface vector. Then you have node connectivity, there will be local to global, so that one to another mapping can be done. So, this is where you get more and more involved in the programming, and programming becomes quite challenging. But the other side of it, or the flip side of it, one can think about that the unstructured system, this is where you have lot of flexibility. So, flexibility is in the sense you can handle any complex geometry. Okay. Having said that, it does not mean that in a structured system you cannot handle any complex geometry. To do that, so in general you cannot do it, but through grid transformation, through grid and equation transformation, one can handle any complex geometry. So, that means also the structured system can be used, but there has to be through transformation. But transformation means not necessarily your grid, your equations, that means the partial differential equations, and all these things need to be transformed in a regular system or the transformed plane and solve it, and then get back to your solution to the physical plane of your complex geometry. So, when you do the transformation, so that also involves lot of challenges. Why? Because you need to do the calculation of your Jacobian, you need to do the calculation of your transform derivatives, you need to do the calculation of your cross derivatives, and that will come with all other associated terms. So, that will make it again bit of challenging. So, in a nutshell, if you think about it, no matter what you do, whether you are in an unstructured system or in the structured system, each of them has certain pros or cons. That means some advantages come with some disadvantages. So, but one has to make some trade off and do the calculations. But if your goal to achieve a solution for a realistic complex geometry, and if you again go back or recall from your first lecture in the introduction, where we have talked about all these applications like flow over car, automobile engines, flow over your aircraft, flow through eyes, human eyes, all these are complex problem, and the problem of that kind of nature needs some sort of a involvement. It is not only solution of some partial differential equation, it requires lot. Lot means for any CFD calculation there are three important stages. One is pre-processing stage, then processing stage, then post processing stage. And again I would like to reiterate here the time which takes primarily the first block and the third block. If I say this is block 1, this is block 2, this is block 3. The first block and the third block takes time. This is when I am talking, let us say one has already developed a numerical code. So, no matter what kind of numerics you have used some sort of a numerics which is fairly acceptable, and using that numeric you have a code. Now, you are about to get a solution done for a realistic system. For example, let us say flow through your blood vessels. So, there will be three stages one has to follow. One is the pre-processing stage, this is block 1. One is the processing stage, block 2. Third block is the post processing stage. Now, pre and post, that means the block 1 and block 3 consumes most of your or bulk of your time for the calculation done. From start to end, these two blocks they consume a lot. Why? Pre-processing stage actually includes your domain definitions, and if your other words in your domain modeling, physical modeling and all these things. So, essentially your physical domain needs to be transformed to your computational domain at the pre-processing stage. That means it involves grid generation. So, whether it is a structured or unstructured, irrespective of that, it involves grid generation, and problem of some realistic nature or complex problem or complex geometry, it actually takes lot of time to generate grid. So, this takes care of your mesh generation, number 1. Number 2, also one has to properly assigns the physical boundary condition to the computational boundary condition, because your code will only read that information. This processing stage, this is where you do the computation, or I would say floating point calculation. So, this part is taken care by computer, and these days you have a high end computers like cluster, parallel processing system, and in a very layman's language, for an engineer those computers are essentially the bulk. They are doing the bulwark for you. The kind of instruction you give them, they will do the work. That means they will just do the number crunching and get back the number that you are looking for, and how that through the set of comments, and that comments means that through your programming, and that programming finally builds to your proper numerical code or CFD code. And once you have given those set of instruction, this guy or the computer will do the work for you. Then essentially it reads all the information from your grid generation stuff. That means your element information, indexing, connectivity, and all these things are done at the pre-processing stage. Proper assignment of the boundary condition. Then you move to the, once your calculation is done, then you need to analyze the data, and that's again consume lot of time, because at the post processing stage, or rather it is a block 3. So that again consumes lot of time, because the data you got you need to analyze, and then only you can correlate with your physical problem. So again this has to be connected with your block 1. That means whatever physical problem I had in hand, and then I have transformed them to a numerical system or numerical problem, solved it, and then the results one has got, whether that makes sense or not. So the post processing stage again takes lot of time, and so in a in a sense, pre and post consumes a lot, the computation part compared to them is less. So this is how one can think about a complex problem can be solved. Now coming back to our discussion, so when we are talking about grid and all these things, this is where we are at the pre-processing stage, and whenever we are talking about the numerics, that is something actually not completely processing stage, but it is a backbone of the processing stage, because the processing stage is the, that means the you are sending some set of commands through your program, and the program does the calculation, and through those algebraic calculations, and those algebraic calculation are the set of equations, and those equations are coming what we have done through the numerics or numerical approximation and prepared those set of instruction. And once you convert those set of instruction to the program, then the theoretically the processing is done at this block. So whenever we are doing those theoretical discussion, that is a part of our processing stage, or the rather the backbone of the processing stage, and those are the calculation should be transformed to the programming. And now when you are at the pre-processing stage, that means the grid, and what we are discussing right now is that structured or unstructured grid and all these, those actually comes under this pre-processing stage, and pre-processing stage takes that kind of effort. Now we have discussed on structural system and the unstructured grid system, their connectivity, their informations, indexing, data structure and all these. So now it would be nice to have a look at what kind of unstructured elements one can have. So one can have different kind of elements. So these are all 3-dimensional elements. So similarly we can have 2-dimensional elements also. Okay, we will see that. So this is one of the tetrahedron, and if you see each of these faces, there are center or centroid, and there are surface vector. So surface vector actually pointing outward, but in calculation, as we have seen, when you do actual calculation, they could be inward also. So this is a example of a tetrahedron, this is an example of a hexahedron, this is an example of a prism element, this is a polyhedral element. Why all these kind of elements would be very handy while generating the grid, because depending on the problem, sometimes you use tetra, sometimes you use hexa, sometimes you use prism. So, all different kind of elements one can use. Now, if you do some sort of a mapping between 3D and 2D, this picture will give you an idea how the 3-dimensional element and the 2-dimensional element are sort of connected. Okay. So, this is a 3-dimensional element of a hexahedron. This is hexa. In 3D we call it hexahedron, and when you come down to 2D, so these are all my 2D elements, these are all my. So, this upper block actually shows all 3D elements, these are some equivalent 2D elements. So, this is quadrilateral. So, that means when I draw a 2D element, it would be a quadrilateral element. Now, similarly, this guy is a tetrahedron. So, this is a tetra in 3D. So, the tetra when you transform to 2D, it actually. So, if you look at carefully, the interesting part here is that when you look at that hexa, it essentially one particular face of hexa becomes a 2D element. Similarly, one particular face of a tetra becomes a 2D element, as a triangular element. This is polyhedral, so this becomes a pentagon, or it could be hexa also, hexagon. So, again this is a one particular face of a 3D element becomes the 2D element. So, that how the connectivity between 3D and 2D element are done. So, now the point comes, when you talk about the elements, there are certain important information there needs to be handled. One of the important thing is that your surface area, okay, sometime volume for 3D, volume of the element, surface area, then centroid, all these require to be calculated. Okay. For any arbitrary element one can do that. So, typically for any polygon the geometric center is, so the geometric center of a polygon is, let us say, xg, which will be nothing but xg, yg, zg if it is in 3D. Now, that will only coincides with the centroid, otherwise not. That means centroid of the polygon, let us say xCE, which is again xCE, yCE, zCE. So, it will coincide with the polygon only for some very special cases. Okay. So, that could be the, I mean, one immediate example could be the triangle. For the triangle, if you look at a triangle, the centroid and the geometric center will coincide. So, that is the beauty of a triangle. Okay. So, now how do you calculate the geometric center? So, the geometric center you can calculate by 1 by k summation of I1 to k by xi. Okay. So, this is where the k is the number of points forming the polygon. For example, if you look at this pentagon 1, 2, 3, 4, 5. So, here k would be 5. Okay. So, the geometric center, again if you look at this, you can have multiple triangles sitting there. So, this is the one which we have connected with line, and you have multiple sub triangle, and the sub triangle will have a centroid. So, there is a polygon center and the centroid of the polygon, and these are the sub center of these things. Now, for this particular smaller triangle or the sub triangle, you can calculate both the geometric center and the centroid. Okay. And then once you do that, while rather doing that, for computing the centroid for computing the centroid of the polygon, you use some sort of a area weighted calculation, area weighted centroid calculation. Okay. Calculation for each sub triangle and summed over the polygon. So, that will get you back the centroid of the polygon. Okay. So, if you write down the mathematics, how it would be looking like, your SF is summation of, this is sub triangle CST, and XC for this would be summation of XCT dot ST divided by SF, and this goes sub triangle C. Okay. So, this is mathematically how you can estimate the centroid of the polygon. So, now you have a, now if you have a triangle, you can again calculate the surface. The reason being, when you look at the centroid of a polygon, so you actually need to calculate the individual sub triangle properties, and then you go over all the, or summed over all the triangle, and then get back the geometric center. So, if you come back to this of a individual triangle, and this is how you define that. This in the coordinate system, x, y, z coordinate system, this is your triangle. It has 3 vertices, 1, 2, 3, and from the center of the reference frame, the radius vectors are r1, r2, r3, which is the standard notation. So, once you say that, then actually you have some, you can calculate the normal vectors at 1, this would be the normal vector, and this is the surface vector, and how you can calculate the surface vector you can calculate like half of R2 minus R1 cross R3 minus R1. Okay. So, that is a cross product. So, this is how you calculate the surface, and the surface vector would be pointing like this. So, essentially this is my triangular, though it is shown in this XYZ framework, but it is essentially this is a 2-dimensional system or 2-dimensional element. This is the triangular face, top of that the thing would be pointing outward normal, and this is how you calculate the surface vector. And if I write that down in matrix form, this is nothing but x2 minus x1, this is x3 minus x1, this will be y2 minus y1, y3 minus y1, z2 minus z1, z3 minus z1. So, in a more generic sense, this is nothing but Sxi Syj plus Szk. So, there are 3 components in each direction. So, essentially we are talking about the surface vector. So, surface vector being a vector quantity, it has 3 different components. If one of them are 0, it will be. So, this essentially the can be, and the what would be the magnitude of the area. So, the magnitude of the area equal to S, this is the surface area, which is nothing but square root of Sx square plus So square plus Hz square. Now, the important point here is that to note the direction of the surface vector. So far while doing this calculation, we have nowhere taken into account whether the surface vector is going to be outward or inward. Now, to find out that, one has to find out that to find it out has to get the dot product of this vector, that means the SF surface vector with the position vector. So, that can give me, so the position vector which or that joins the centroid of element CE to the centroid of the surface C small e. Okay. So, once you do that, if the sign of this dot product is positive, that means this will be outward directed or outward pointed. If the sign of this is negative, that means it will be inwardly pointed. So, the one hand you get the calculation of the surface vector, then once you get the calculation of the surface vector, you find out the direction of the surface vector. So, these are the 2 important things one has to have, and if you just recall from your unstructured grid system, you need to have both the calculation of the vector and their dot product. Now, for a 2D system, if you consider a 2D grid, okay, the area or the surface area, this is or something which surface area which will actually represents the volume of the control cell, okay, with volume of the control cell with uniform depth or unity depth, with unity depth. That is how a 2D triangle can be looked at. It represents the volume of that or the unity depth out of plane essentially in the third direction. So, you can find out the volume of a triangular cell, that you can calculate as this is V. V is half of R2 minus R1, R3 minus R1, the magnitude, which is essentially x2 minus x1 into y3 minus y1 minus x3 minus x1 into y2 minus y1. So, if I write, it is x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. Okay. Now, again the sign concern will be issue, and that will depend on the orientation of the vertices, that is 1, 2 and 3. If they are oriented in a counterclockwise direction, this will return a positive sign. If they are oriented in a clockwise direction, this would be a negative sign. So, the sign convention will also be an issue. So, we will stop here today and we will take from here in the follow up lectures.